So good morning, everyone, and welcome to the first Earth Institute coffee morning of the trimester of the new academic year. I'm actually going to have to shoot off in a moment to go to a school meeting, but I just wanted to sort of drop in at the beginning and welcome everyone back, and to thank Shane for taking on the role of chairing the coffee morning, and to thank Budi for giving the coffee morning talk, and to welcome him to the Earth Institute. He's one of a number of new members that we're welcoming at the end of this summer. So thanks very much indeed, Budi, and thanks Shane, and thanks to all of you for attending. And I look forward to staying for the whole of next week's coffee mornings at Ash this time. So thanks very much. I'll hand over to Shane. All the best.
Thanks, Taz. Yeah, and welcome everyone. Yeah, to the first Earth Institute coffee morning of the new academic year. Our host today is Dr. Budi Zhao, who is a colleague of mine in civil engineering and joined us in August 2020. And before he arrived in UCD, Budi worked as a research associate in Imperial College London for a year, I think, Budi, following 2 years in Saudi Arabia in King Abdullah University of Science and Technology. And I think, Budi, you're planning to give us an overview of the energy climate challenge and discuss how your research and geomechanics research in general can contribute to tackling this challenge. So over to you, Budi.
Thank you, Shane, and welcome everyone to join this event. Let me start to share my screen. So first of all, it's a pleasure and honor to join the Earth Institute with so many excellent, colleagues on different research areas for energy and climate challenge. So in today's event, I will briefly share my view of how, as geotechnical engineering, engineers can help tackle the energy and climate challenge. So my name is Budi Zhao, and I'm an assistant professor on geotechnical engineering from the School of Civil Engineering in UCD. Just try to. So I believe that the energy and climate challenge will be the major challenge for us in the next few decades. And in geotechnical engineering, we have, I think we could help to develop some critical techniques that can help us to tackle this challenge. So here are 4 examples. The first example is the offshore wind. So offshore wind is a renewable energy that can help to decarbonize the energy sector in Ireland and in the world. For example, in Ireland, the potential offshore wind close to Ireland can provide about 7 times the electricity consumption every year. And in geotechnical engineering, we could provide increase the design method to reduce the cost and increase the safety of the offshore wind foundations. The second technology I want to mention here is the nuclear waste disposal. Although this seems not to be an issue in Ireland, but I want to say nuclear energy is one of the main renewable energy that can decarbonize our energy sector. And the problem is we need to deal with the nuclear waste. So here's one major approach, that we dump the nuclear waste into this large copper container and bury it into the deep earth. So we have to apply this type of bentonite clay surrounding this copper container to prevent the nuclear waste leakage. So the deformation of this bentonite clay will play a critical role in making this technique safe. The third technology I want to mention here is carbon geological storage. So in this technique, we can capture the CO2 from large electrical power plant or other major plants, and then inject the CO2 into the deep earth and store it safely for thousands of years. So we need to understand how CO2 will react with the initial fluid in the reservoir and how we can prevent the CO2 leakage. And lastly, due to climate change, we are expecting more frequent extreme weathers such as heavy rain. And we need to increase the resilience of our geotechnical infrastructures to prevent some catastrophic disasters, such as the embankment dam failures. So that's the general background of my view in sustainability and geomechanics. So here's one specific example. In carbon geological storage, we capture the CO2 and compress it into a high pressure and then inject the liquid form of CO2 into deep earth. For example, in deep saline aquifer or depleted oil and gas fields. For example, in Ireland, there is currently a Kinsale Height gas field, which has been planned for the CO2 storage site. Now, the goal is to safely store billions of tons of CO2 underground for, let's say, 10,000 years. And so when you inject CO2 into the deep earth, the CO2 will displace the original water, saline water in the reservoir. And then it can generally lead to the drying of the salinity water. And then this can lead to some mineral precipitation. So the mineral precipitation will block the pores, which reduce the permeability of the reservoir rock. And then it can reduce the injectivity of your well. And of course, we don't want that because that means we lose some money and that's spent on drilling the well. And secondly, the mineral precipitation can apply a huge crystal pressure onto the rocks that can eventually lead to some failure close to the injection well. Now, that is kind of hydro-chemo-mechanically coupled process in geomaterials. And to be honest, what are these? It seems to be complex. And what is the hydro-chemo-mechanical coupling? So we are all very familiar with Hooke's law, which describes the mechanical behavior of a single spring. Now, when you apply a dead load to this spring, you will see the deformation of the spring. So we have a simple equation. On the left-hand side, we have the force applied to the spring. And on the right-hand side, we have the stiffness of the spring and the deformation of this spring. So we usually use a metric form to describe the mechanical behavior of geomaterials, such like soils. And we have the stress on the left, and we have the stiffness matrix on the right, and the strain. So when you have the hydraulic behavior here, now you see here is the hydraulic pressure, and this is the permeability, the material property, and here you have the flow field. Now, the mechanical and hydraulic behavior are coupled. So for example, when you inject fluid into with a very high pressure, you may eventually lead to the hydraulic fracture, which can crack the rock. On the other hand, once the rock is under a high stress, and then it can deform and lead to some fracture, and that fracture will increase the hydraulic permeability of the rock. So you see, this is a hydromechanically coupled process. Well, it becomes more complex when you have chemical factor. So for example, you can have mineral precipitation that clogs the pores, reduce the permeability, and then the crystal pressure can deform the rock and lead to some fractures. So here are 4 examples of my previous study on different types of hydro-chemo-mechanical behavior of geomaterials. And the first one is a particle crushing. So this is a single mechanical property of a single sand particle. And you can see the particles under high stress level, it can break into several fragments. And then we can see that the particle shape and size have a different variation. The second example is a hydro-mechanically coupled process in fan sediments. So when fan soils, let's say clay, dries, it will tend to reduce its volume, and then it can lead to some desiccation cracks. So this black curves are indicates the desiccation cracks that can increase dramatically the hydraulic permeability of the fan soils. The third example is a fans migration. So you see the circular discs. These discs are simulating the porous media. And you see the black dots. Those are the fan particles that can move through this porous media and can eventually form some clogging events that reduce the permeability of this porous media. And the last example is a mineral precipitation process. So initially, this is a porous media that is saturated with high salinity brine. And when it dries up, air starts to invade the porous media, and we see some mineral precipitation occurs in this porous media. And we can clearly observe the crystal growth and air invasion process. So in my research, I mainly adopt the non-destructive imaging techniques to monitor the hydro-chemo-mechanical process in geomaterials. So there are many. This type of electromagnetic waves, from the radio wave to gamma ray. The frequency of the electromagnetic wave will increase, which means a higher photon energy and higher penetration depth into the materials. So I have been mainly adopting three types of techniques. The first one is the nuclear magnetic resonance and MRI, which adopts the radio wave to image the saturated porous media. The second technology is a combination of optical microscope and microfluidic chip, which use the visible light to visualize the process in a transparent porous medium. Now, the last technique, which has been used for last 10 years also, is the X-ray macrotomography. So this technique can penetrate through materials and then can see what is happening internally in your sample. So using that non-destructive imaging techniques, I developed many in-situ loading apparatus, which means that the apparatus can operate within this, let's say, X-ray CT scanner, so that you do not need to move in and out your sample, which may lead to some disturbance of your sample state. So the first example is a single particle compression apparator. So as you can see, we have a stabbing motor to apply the vertical load. We have a load cell and LVDT to measure the force and displacement applied on this single sand particle, which is about 1 millimeter size. Now, during the compression test, we could apply the X-ray CT scan to characterize the 3D 3D view, to have the 3D view of the sand particle behavior crashing process. The second technology, second apparator is a high pressure odometer test. So in this apparator, we apply one-dimensional compression test to hundreds of sand particles. Instead of one particle, we apply the load to hundreds of particles. And then we can differentiate individual sand particles and see how that evolved during the high compression load. The third apparator is a desiccator. So in this apparator, we apply a constant confining pressure to fine sediments and then allow it to dry, so that we use X-ray CT to monitor the drying process and how desiccation crack can form even, let's say, in the subsurface. The second example is the macrofluidics. So this is a very small shape, and it is usually millimeter size, and you have this some particles of macron size and the channels, predefined channels within these macrofluidic shapes. And then when you you can inject fluids. So in this case, we inject the fluid, the particle suspensions, which means fluid and the macro-sized particles, into these macrofluidic shapes, and then we can use the microscope and a camera, digital camera, to capture what is happening inside this macrofluidic shape. Now, the third technique is the nuclear magnetic resonance. So here, with this type of technique to monitor the internal process in soils or rocks, we can apply a high temperature, and we can inject water into the sample, and then we can apply confining pressure to on the sample. At the same time, we use AMR to monitor what is happening internally. So next, I will show probably 4 examples and typical results from different studies. And so the first example is relevant to offshore pile foundations. So for the offshore soils, there are some crushable sands that when you apply pile penetration into the soils, you will expect some sand particle crushing. And the sand particle crushing will eventually reduce the pile resistance, and that can change your design methods. So here we test one single sand particle, and here you are looking at the vertical slide in the middle of a single sand particle. And then we start to load the sand particle, and then we image the sand particle 3 times during the loading test. So S1 is the first scan before the crushing, S2 is after the first peak load, and S3 is after extensive fragmentation. So then we can use image processing to get the 3D morphology of the sand particle and its fragments. And then we can quantify the particle evolution, particle shape and size evolution during this process. The second study is about desiccation crack formation in fine sediments. So this is relevant to nuclear waste disposal. As I showed before, you have the bentonite clay surrounding the copper container, and then the nuclear waste will generate some heat that will eventually dry up your bentonite soils, and then that can lead to some desiccation crack and increase the permeability. So that may eventually lead to some nuclear waste leakage event. So here you are looking at a horizontal slice of kaolinite specimen during the drying process. So we perform the drying test of the kaolinite sample for about 100 days. I think it should be more than that. And then we have the confining pressure on the soil. At the same time, the soil is drying, so it tends to shrink. And then we see how the desiccation crack, this is the black lines that indicate desiccation crack, occurs in these fine sediments. Now, the third example is the air invasion and mineral precipitation process in porous media. That is relevant to carbon geological storage, which means when you inject CO2 into the porous media, you eventually will dry the brine, and that leads to the mineral precipitation. So as you can see, we have the mineral precipitation initiated in this porous media, and it starts to grow in this porous media, and eventually it forms to this type of pattern. So with this macrofluidics, we can design the pore topology of the porous media, and then to investigate different, to articulate different properties of the porous media that influence the mineral precipitation and air invasion process. So the last example is advanced migration and clogging. So, so this is relevant to embankment dam instability. The idea is when you have a heavy rain that generates some water flow internally in this embankment dam, and that may bring some soil particles inside this inside this embankment dam body, and that can change the fabric of soil and eventually leads to the embankment dam instability. So here we define the macrofluidic shapes with this type of porous media, and then we see how the glass particles and the latex particles transport in this porous media, and how this eventually form clogging events. And we observed very different clogging mechanisms for glass particles and latex particles. Yeah, to sum up, I think my research can be summarized in this single chart. So I want to do some energy and environment related geotechnical research, so GEGE. And the first component will be on the granular materials, which characterize the particle shape and the particle breakage, and that is relevant to offshore piles and railway blast problems. And the second component is more about fine sediments. So fine sediments have totally different behavior because internally it has a very small size. And I have worked on desiccation cracks and pore space characterization with nuclear magnetic resonance. And those studies are relevant to clay liners, such as nuclear waste disposal and earth-filled dams. And the third component is a multi-phase flow problem. So I have been working on fast migration and mineral precipitation. So those problems are relevant to geothermal energy, CO2 geological storage. And lastly, this is a new component that I wanted to develop in UCD, that is about smart geotechnics. So I want to develop some cheap sensors that can be applied to offshore foundations and slope stability monitoring process. And then we can use the inverse analysis and the data collected from the sensors to provide a site characterization and monitoring. So for all of my research, I want to have a strong engineering relevance on geotechnical engineering problems. And then I want to use my research to provide a new physical insights into those different kinds of problems. Thank you for your attention.
Thanks, Buddy. That was really interesting. Some really good stuff there. And yeah, shows I suppose the direction of where we're going in many ways in kind of the geotechnical area in civil engineering. So that's great. Thanks for that. I might open the virtual floor for questions. If anyone has a question, please work away. See if I can. You might stop sharing your screen there, Buddy. Is that all right?
Yeah.
Right. Yeah. So does anyone have any questions there, folks? I think I can see everyone now.
Yeah.
I might start, Buddy, then, if that's all right.
Yeah.
So on the clogging issue in embankment dams, is there some way that we can monitor in situ? Obviously, you've done quite a bit of work in the lab and on modeling, but is there some way we can in situ assess the issue of clogging in these embankment dams?
Yeah, I have read about some geophysical methods that can monitor in-situ, and I'm thinking about developing a low field and low cost nuclear magnetic resonance sensor to be implemented into the embankment dam. The problem is this can happen at any place in this embankment dam, so it's very difficult to say, okay, which place I want to put these sensors on this embankment dam. So I think we need more research to evaluate what is the location of the embankment dam that with the highest risk to develop internal erosion problem, and then we can probably have a better view to put those sensors.
Yeah, no, you're right. I mean, the structures are so heterogeneous; they are so variable, really. But I mean, there are areas that the infrastructure owners will be aware of that they may have already, they may already have a sense that there are issues in terms of internal erosion. So actually having a test site initially, I suppose, to test your methods where that there are problems might be a good idea. Actually, we have a couple of projects where I must get you, I might get you in touch with Network Rail, for example, who have a couple of sites where internal erosion is a bit of an issue. So I think that would be
that sounds perfect. Thank you, Shane. Yeah.
So in terms of NMR, then so what exactly are you trying to measure? So to the low cost sensor. So I assume then your depth range with the NMR small sensors will be quite small. So near surface changes is what you're looking at here.
Yeah, NMR is a fantastic tool. Has been applied to many areas. In geotechnics, it's a kind of new area that we haven't explored yet. So NMR provides, it can monitor, it can get the signals from water molecules that in very small pores, in nanometer pores. So that's why with X-ray CT, we cannot see what is happening in fine sediments. Let's see, with 1 micron size kaolinite particles, you cannot use X-ray CT to see what is happening internally. So with NMR, we could monitor what is happening in fine sediments. But as you mentioned, the size of the monitoring area is quite small, because you have a very small magnetic field surrounding this NMR. So yeah, that's definitely something that we should. So there are some techniques can use Earth magnetic field. So with that technique, you can monitor a very large area. That's the hundreds of meters area. So
yeah, no, I guess it depends, Buddy, how when we talk about low cost, it's how low cost you can make these kind of sensors in a way, because if they're relatively low cost, you can obviously install quite a number. So yeah, then you can cover quite a large area then potentially. So no, it's all very interesting stuff actually. Does anyone have any other questions, folks? Not sure there's any there. In terms of the kit, Buddy, do you have access to the kit or in UCD? I know obviously we don't have kind of the NMR and some of the other non-destructive methods you mentioned, but do we have access to some of the kit that you can use?
What do you mean by case?
Well, so how do you source the NMR apparatus and any of the other non-destructive methods that you're testing?
Yeah, I say Cersei is here. So X-ray CT, we have some facilities in UCD, and microfluidics, we have Fraunhofer Research Center in DCU. For NMR, I haven't been able to sort out where I can get these devices. I'm currently collaborating with a professor in China, and he is from electrical engineering, and he actually developed those low field NMR sensors. So he has been working in this area for 20 years. So the idea is they will develop this NMR sensors, and we will apply to geotechnical applications. And actually, my PhD student has already visited their group to test their NMR sensors for CO2 carbon capture storage, carbon geological storage project, and the result seems pretty good.
Okay, very good. Yeah, and Saoirse just posted into the chat there that there are 2 world-class X-ray CT scanners in UCD and accessible to all. So that's fantastic. And obviously, Buddy, you've been in touch with Saoirse.
Yeah, actually, just to mention the particle crushing image that I showed in the presentation is identical, is obtained from an identical CT scanner that we have in UCD.
Okay, brilliant. That's really helpful, actually. Does anyone else have any questions, folks, before we draw to a close? Patrick?
Yeah, I just have a comment. So I'm from politics and international relations, so I have nothing sensible to say, but I just say hello to Buddy, and it was a great presentation, and I enjoyed it, and I'm going to think about it. So thank you.
Thanks, Patrick. Yeah, no, it was very,
thank you, Patrick, for the positive comments. Yeah, I'm always when looking at the climate and energy issue, it's a bigger area, and I think it's very important to discuss with people from different areas, like say politics or economics, to have the general view, and which is important to direct my research.
Yeah, congrats, thank you.
Thanks, Patrick. So unless there's any more questions, folks, I think we'll just post it there in the chat. So next week's coffee morning is on fishing for genome to ecosystem linkages in North America's aquatic endemicity hotspot. Hope I pronounced that right. From Darren Hulsey from Biology and Earth Science. Okay, so thank you very much. Toby, did you have a question?
Thank you, everyone, for coming.
Before we go, no.
Just to say hi to Budi.
Hi, Toby. Yeah, nice to meet you here.
Nice to meet you.
Thanks, guys. See you next week.